Imagine you are asked to find the Maclaurin polynomial of degree n equals 5 for f of x equals sine x. So what's happened here is that you are trying to find some polynomial that will approximate the function sine of x. So the first thing you notice, or you should be looking for, is what degree are we looking for, and it's n equals 5. To me, the first thing that tells me I'm going to need to do is actually find the first 5 derivatives of sine of x. So I'll start with the original function, f of x equals sine x, and then I'll start taking derivatives. So the first derivative, f prime of x, is the derivative of sine x, which is cosine of x. Then I'll do my second derivative, is a negative sine x. My third derivative equals a negative cosine x. My fourth derivative equals a positive sine x, and you can see that I'm back at the beginning. So my fifth derivative is equal to cosine of x. So I have all of the derivatives I'll need because I could have up to 6 terms for an n equals 5. So the next thing you look at is where is it centered. And this one says it's Maclaurin, so it is centered at c equals 0. So I need to actually evaluate each of these when x equals 0. So sine of 0, f of 0 equals 0. F prime of 0 is cosine of 0, and that's 1. F double prime of 0 is 0. The third derivative of 0, negative cosine of 0, is a negative 1. The fourth derivative at x equals 0 is 0, and then the fifth derivative at x equals 0 is 1. So this tells me part of my coefficient. Now, following the pattern for a Taylor polynomial, and this one's Maclaurin, so it's just a special case where it's centered at 0, I would say the fifth degree polynomial of x equals, and I'm going to follow a pattern. So I'm going to take my f or f prime, f double prime value, so I'm going to start with 0. Then it's multiplied by x minus where you're centered. Now this is Maclaurin, so 0 to the 0th power over 0 factorial for that very first term. Then now I'm looking at my first derivative, so 1 times x minus 0 to the first over 1 factorial, plus 0 times x minus 0 squared over 2 factorial, I'm to here. The next one will be a plus a negative 1 times x minus 0 to the third over 3 factorial, plus 0 times x minus 0 to the fourth over 4 factorial. And then the final term begins with a 1, so plus 1 times x minus 0 to the fifth over 5 factorial. And then I'm going to simplify this. So 0 factorial is defined to be 1, but when I multiply 0 by anything, this is gone. So this is going to go away, goes to 0, so does this, and that one. So all of my even terms, 2, 4, and then the 0th term are gone. So my piece of 5 of x is not going to have 6 terms, it's going to have 1, 2, 3 terms. X minus 0 to the first is x, times 1 is just an x, divide by 1 factorial. 1 factorial is just 1, so this equals x. Then I'll have a negative x cubed over 3 factorial plus x to the fifth over 5 factorial. So this polynomial will match sine of x up to a point. But if you want to know how much you're off by, you can actually just plug in some values to see. Now, the closer to where you're centered, the better the estimate this should be for your actual polynomial. So if we wanted to check, say, piece of 5 of 1.2. So we're not that close. In math terms, you can get a lot closer because I could be using this to estimate at 0.2 or something like that. But piece of 5 of 1.2, I could take 1.2, use my calculator, plug it into this, and I would get a decimal approximation of 0.932736. If I actually do f of 1.2, that's equal to sine of 1.2, and that comes out to 0.932039. So the difference between my estimate and what it actually is called the error, and the error is symbolized by, it's the absolute value of f of 1.2 minus p sub 5 of 1.2. And all this is looking at the difference between the two. The absolute value is there because we really don't care if we're off by a positive amount or a negative amount. We just want to know how much we're off by. So you would subtract the two numbers, then ignore it if you get a negative, and the amount we are off by is 0.000697. So rounded, it's about tens, hundreds, thousands, about 7 1,000ths, I'm sorry, 10,000ths, tens, hundreds, thousands, 10,000ths. About 7 10,000ths is what you're off just by doing a fifth degree polynomial. If you go a little farther out, let's say you do p sub 5 of 2.1, that comes out to 0.896842, and then f of 2.1 is approximately equal to 0.863209. So if I look at the difference here and subtract, the error comes out to 0.033632. So you can see it's fairly small. In math terms, that's huge, but the error here is 7 10,000ths, and here we're a little bit more than 3 hundredths. So the error is increased greatly just by moving a little bit farther from where it's centered. And again, Maclaurin was centered at c equals 0.